Hi. Yep, sounds good. Hi guys, my name is Samuel Jasper. I'm from CSC department. My topic for AIT for differential equations and vector calculus is on change of order of integration over circle. Integrals over circular regions. A double integral over a circular region involves integrating a function f of x and y over a region R that is a circle in the plane. To handle this type of integral, it's often convenient to switch to polar coordinates because the boundaries of the region are naturally circular and the geometry simplifies in this system. Polar, polar coordinates. In polar coordinates, a point x and y in the plane is described by x is equal to r cos theta and y is equal to r sin theta. The differential area element dx dy in Cartesian coordinates becomes r dr d theta in polar coordinates. Double integral in polar coordinates. A double integral over a function f of x and y over a circular region R can be written as double integral R f of x and y dx dy is equal to integral of theta 1 to theta 2 integral of r1 theta to r2 theta f of r cos theta comma r sin theta r dr t theta, where r1 theta and r2 theta define the radial bounds of the region from each angle theta. Theta 1 and theta 2 define the angular bounds for the integration. For example, we have a question here. Evaluate the double integral of f of x and y is equal to 1 over a circular region of radius r centered at the origin. We have given double integral r1 dx dy. In polar coordinates, the double integral becomes integral of 0 to 2 pi and integral of 0 to r dr d theta. Now integrate. Integrate with respect to r. Now, when we integrate with respect to r, the integral becomes 0 to r dr is equal to r square by 2 limits r to 0. The product we get is r square by 2. Now, if we integrate the product with respect to theta, then the integral becomes 0 to 2 pi r square by 2 d theta. As we are integrating with respect to theta, the products and the answer we get is r square by 2 multiplied with 2 pi. The answer we get, the final answer that we get is pi r square. Understanding the double integral. A double integral is an extension of a single integral used to compute quantities over two-dimensional regions. It can be thought of as a way of summing up small quantities over a region in a plane. Specifically, a double integral is used to compute things like the area of a region, the mass of a lamina with variable density, the volume under a surface. The basic concept. The double integral of a function f of xy over a region R is written as integral double integral R f of x and y dx dy. This notation represents integrating function f of xy with respect to x and y over the region R of R. The value of the double integral can be interpreted as the volume under the surface z is equal to function of f of x and y and above the region R in the xy plane. A generalization of finding the area under the curve, but for a surface over a two-dimensional region. 2. Integrated integrals. In practice, the double integral is usually computed by breaking it into two separate integrals, one for each variable. This is called as an integrated integral. and it involves performing one integration after the other. For a region R, the double integral can be followed or can be often be written as double integral R function of f of x and y dx dy is equal to integration of y1 to y2 and integration of x1 y to x2 y function of x of y function of f of x and y dx dy, where here the integral integrates with respect to x while y is held constant. The outer integral integrates with respect to y with with respect to y after solving the inner integral as we inner integral. We have did this method earlier. 3. Geometric interpretation. The double integral can be interpreted geometrically as a volume under the surface z is equal to function of f of xy and above the region R. If the function f of xy is positive, the integral gives the volume of the region under the surface. If the function f of xy is negative, the integral gives a volume below the surface. If f of x with the function f of xy is equal to 1, the double integral represents the area of region R. If the function f of xy represents a density function, the double integral gives the total mass of the lamina with the density over the region R. Evaluate the double integral of function f of xy is equal to x plus y over a square region R is equal to set of 0, comma 1 multiplied with set 0, comma 1. We are integrating over the square, so the limits are constant. So when we apply double integral r x plus y dx dy, the first integral becomes 0 to 1 and the second integral becomes 0 to 1 x plus y dx dy. Now first we will integrate with respect to x and then we will integrate the product that we got with the uh, with respect to y. Now let's integrate with respect to x. Then we'll get 1 plus 2 plus y. Now if we integrate this with respect to y, then we will get the answer as 1 as we did here. Thus the value of double integral is 1. Standard order of integration in Cartesian coordinates. In Cartesian coordinates, the standard order of integration for a double integral typically follows one of two common patterns: integrating with respect to x first and y second, or else vice versa. Order f of xy dx dy. This order is most commonly used when the limits of integration are straightforward or when x depends on y. The outer integral integrates with respect to x and the inner integral integrates with respect to x. Order 2 f of xy dy dx. This order is typically used when the limits of y are easier to express in terms of x or when the region is more naturally described in terms of y. The order of integration depends on how the region R is described. For rectangular regions, the limits are constant. So, the order doesn't matter as much. The region is described as a product of intervals like R is equal to set of A, comma B or multiplied with set of C, comma D. And R is this some typing mistake. For non-rectangular regions, the order depends on the boundaries. You need to choose an order that makes the limits simpler to express. Let's consider that the region R is equal to A comma B multiplied with C comma D, which is a rectangle, and here the limits of integration of both x and x and y are constant. Uh, The limits of x are from a to b and the limits of y are from c to d. Then the double integral looks like this. This is the standard order of integration for rectangular regions. Changing the order of integration. Changing the order of integration in a double integral is a technique used when it is difficult or complicated to evaluate the integral in its current order, but easier in reverse order. The process involves swapping the limits of integration, and it requires careful attention to the geometry of region of integration. When to change the order of integration? When the region is described more simply in terms of the other variable, or the limits of integration are difficult to express in the current order. Why to change the order? It simplifies the integral. The integral is simpler in the newer order. The integral becomes easier to compute with the newer limits, and the changing of the order of integration in the double integral can be a powerful technique to simplify the evaluation process. And is also used to avoid complicated limitations. In some cases, the limits of integration might involve complicated expressions of piecewise functions. Changing the order of integration can simplify these limits, particularly when the region is not easily described in the original order. It is also used to match the geometry of the region. For instance, if the region is a triangle, it might be more natural to describe it by fixing y first and varying x, rather than the other way around. Using polar coordinates for circular regions. Using polar coordinates is a powerful method for simplifying double integrals, especially when dealing with circular or radial symmetric regions. In polar coordinates, we switch from the rectangular coordinate system convention to one based on r, the radial distance from the origin, and theta, the angle from the positive x-axis. Basic formula for polar coordinates: x is equal to r cos theta, y is equal to r sin theta for the function of f of x and y to polar coordinates r comma theta. Double integral in polar coordinates. If we substitute the x is equal to r cos theta and y is equal to r sin theta, then the function becomes in this way. The advantages are for this polar coordinates is the integral often becomes easier to evaluate when the region is circular or sector shaped. Advantages: its simplification of the integral, and it is simplified geometry, and regions with radial symmetry like circles or sectors are much more naturally described in polar coordinates. If the problem involves such as shapes, the limits in polar coordinates might be simpler or more intuitive. Conclusion: changing the order of integration, especially in polar coordinates, can significantly simplify the process of evaluating double integrals, particularly when dealing with regions that exhibit radial symmetry or circular shapes. Polar coordinates are particularly advantageous for problems where the region of integration is a disk, sector, or has rotational symmetry. Simplified geometry. Polar coordinates naturally describe circular and sector-shaped regions with simpler bounds, making the setup of the integral easier. Easier integrals are the functions like x square plus y square, x square plus y square into x square plus y square, which transfers into square, r square, r square. And exploiting symmetry. Polar coordinates helps to exploit the natural symmetry of the region, making the integral more straightforward to compute. And it's also efficient computation. Changing the order of integration or switching the polar coordinates can reduce computation complexity. By changing the order of integration or converting the polar coordinates, you can streamline the process, especially when the integrate or the region has circular symmetry. This is a powerful tool for simplifying complex integrals, particularly in physics, engineering, and any other fields. Thank you. Thank you.